Yeah, the last part of the chapter deals with types of collisions. First is an elastic collision, perfectly elastic collision. Collisions that occur and the total kinetic and momentum before and after the interaction will be the same. Perfectly elastic collisions. When you're talking about a perfectly elastic collision, your momentum and your kinetic energy prior to interaction will be the same as your momentum or kinetic energy after interaction. A golf ball bouncing off the ground. It's not quite perfectly elastic, but it's a good example of close to elastic collisions. If I take a look at the spring-loaded carts here, your momentum or your kinetic energy prior to interaction will be your momentum and kinetic energy after interaction. The velocity right before impact here, through the spring will give you the velocity after impact of the spring. Once again, we're talking about an isolated area. So when I move that, whatever my velocity is prior to hitting is going to be my velocity after hitting. Okay, and I should travel close to about the same distances for each of these. Okay, so when you take a look at perfectly elastic collisions, what you're talking about is conservation of kinetic energy and momentum. Conservation of kinetic energy and momentum. Okay, we just got done with the Winter Olympics. I don't know if you watched any of it, but the curling, the guys that throw the things and they do the curling and then they start sweeping the ice in front there. When those things impact each other, that is close to having a perfectly elastic collision. Okay, it's not going to be exactly perfectly elastic, but it's going to be close. The velocity right before impact equals the velocity right after impact. And once again, you have your total kinetic energy and momentum are conserved, which means 1/2 mv1 squared plus 1/2 mv2 squared is equal to the exact same things after collision. Once again, your prime means your velocity after collision. Or m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Your V is your prior to collision. Your V prime is after collision. Okay, so when you look at just your V, that's your velocity prior to collision. Your V prime is your velocity after collision. Perfectly inelastic collisions, collisions in which two objects stick together after colliding. They stick together after colliding. So it'd be like having these two cards, and I would have a big wad of gum on one of the cards. So when they collide, they stay together. That would be perfectly inelastic. Realistically, your collisions are somewhere in between perfectly elastic and perfectly inelastic. Only momentum is conserved in perfectly inelastic collisions. So momentum is only momentum will be conserved in all collisions. Kinetic energy will not be conserved in anything except for perfectly elastic collisions. Because what you will have is in outside, other than perfectly elastic collisions, you're going to lose some energy, thermal energy. Bonds will be, whenever you crinkle something, when something gets dented in, what happens is bonds are broken. Okay, whether it's if you have two cars that hit each other and you get dented in, okay, the metal has bonds that are broken. And when bonds are broken, you have thermal heating that exists. You have some thermal energy that's going to be released. Okay, you'll have friction. So when you're dealing with perfectly, or when you're talking about inelastic collisions, kinetic energy is not kinetic energy is not conserved because you lose the thermal energy. Whenever you have collisions not perfectly inelastic or perfectly elastic, you lose thermal energy. Once again, when you get collisions, you have friction, you have bonds that are broken, all that adds into thermal energy, so you don't conserve the kinetic energy. So kinetic energy is not conserved in inelastic collisions. Energy is converted into non-mechanical energy. net non-mechanical energy, sound, thermal energy, like I said, bonds that are broken. Whenever you hear a collision that occurs, sound waves are going out. Well, something has to create energy for that sound wave to come out. So you have a non-mechanical energy that is a sound wave. Most collisions in life, most collisions in real life are neither perfectly elastic nor inelastic. Two football players, they collide. Somebody comes after another one, and they hit, and they look to tackle. Okay, there's a sound that is being released. You hear the sound of the tackling out there. Once you hear the sound of the tackling, even though somebody will tackle, somebody they will grab and they will wrap and they stick together, there's still sound that's occurring, which means you have energy that's being released in sound waves. A golf ball doesn't rebound to its original height. Okay, it bounces, but it's not going to come up to its original height. If I had a golf ball, that's what I was looking for. If I bounced a golf ball from here, I would release it, hit the ground. It would come back to about right here, then about right here, then about right here. Eventually, if I let it continue to bounce, it would bounce and then just stay on the ground. But when you talk about a golf ball, those are fairly inelastic or fairly elastic. Okay, it's how they are developed. They can't be perfectly elastic because if they're perfectly elastic, that means whenever I would hit a golf ball, it would go very far. And we would all be professional golf players. Okay. A bullet of mass of 6 grams is fired into a 1.25 kilogram block of wood at a speed of 758 meters per second. Upon impact, the bullet lodges itself in the wood. The block of wood sits on the back edge of a 1.5 meter tall table. Upon impact, initially travels horizontally off the table and impacts the ground below. What's the velocity of the block after impact? How far from the table will the block impact the ground? So this is our setup. We have a block of wood on top of a table. Okay, this table is 1.5 meters above the ground. We have a bullet that is traveling at 758 meters per second. And the mass of this bullet is 6 grams. And it's being fired into a 1.25 kilogram block. We want to know it's initially stationary. After impact, what's the velocity of the block and the bullet, and then how far on the ground is it going to fall? Because this will hit and then fall to the ground. Well, the bullet is being shot and lodged itself in the block of wood. So we can classify our collision as perfectly inelastic, or an inelastic collision. This is an inelastic collision. So if it's an inelastic collision, that means the only thing that's being conserved is momentum. Kinetic energy is not being conserved here. So only momentum is conserved. So if momentum is conserved, we have mv1 plus mv2 has to equal mv1 prime plus mv2 prime. Now, it doesn't matter which one you have here. Okay, is M1 or V1, doesn't matter if you say this is mass 1, this is mass 2, doesn't matter. I'll say the bullet is mass 1. So we have the mass of 6 grams. Here we have a mass of about 1.25 kilograms. Okay, we have an issue there because one's in grams and one's in kilograms. So we need to be able to convert into either grams or kilograms. I'm going to go into kilograms. 6 grams is 0.06 kilograms. 0.06, my bad. So if I look at prior to interaction, I have a bullet traveling 0.006 times a velocity of 758. The block is stationary, so does the block, what happens to the MV2? Do we have any, yeah. Zero, yeah. We don't have any momentum here, because it's just sitting there. But if I look at the right-hand side of the equal sign, what can we do now with respect to our masses? Because one mass is going and sticking in to the block, and they're both falling to the ground. What can I do with my two masses here? Add that together. So what we really have is we have an M, one mass, and one velocity. So we have both the masses that are stuck together and just one velocity. So we have our 1.25 plus the 0.006 times our velocity. So our velocity after impact is what, Amber? 3.62 meters per second. Good. Okay, so a 758 6 gram bullet traveling 758 meters per second has been slowed down to 2.62 meters per second. But the object will fall then from our tabletop. We have an initial velocity horizontally of 3.62 meters per second. We want to find out what is this distance that it will travel and hit the floor below. What we now have is we have trajectory motion. So we have vertical and horizontal. We have initial velocity of 0 vertically. We have acceleration of gravity we know a distance or displacement. We don't know the time or a final velocity. But what we have is we have trajectory motion. So we go back into our trajectory motion ideas. Anybody remember what we solved for first? Here we have it horizontally, we have an initial velocity of 3.62 meters per second. We have no acceleration. We don't know displacement time or V final. Anybody remember what we did first? Solve for time using our vertical component. Okay? So we solve for time using our vertical component. Displacement is equal to V initial t plus 1/2 AT squared. We have no initial velocity. But we have acceleration and we have displacement. And we can solve for time. What do you get, Grace, for time? All right. Multiply by 2, divide by negative 9.81, square root. Possibly come up with 0.56. 0.56. That's seconds. Multiplying by 2. We have -3, and then divide by that 9.81. Then we take the square root of that, 0.56. So that is my time over here, 0.56. So it takes 0.56 seconds to be able to drop down here. But it's also, as we talked about, 0.56 seconds to go over there. So horizontally, we can take a look at displacement. We have an initial velocity horizontally. We do not have acceleration. We don't have acceleration, but we have an initial velocity horizontally and a time. So we take our answer and multiply it by 3.62. Okay, then what do we come up with?
2.03.
2.03?
Yeah.
2.03 meters. Okay, so that will be your distance that it travels horizontally. Oh, I think we will stop there today. See what you can do with this last problem here. Okay, see what you can do with the last problem. We'll start with that tomorrow. Questions? I mean, think about the inelastic. If I drop this roll of tape and it hits the ground, it's not going to bounce up, but what you hear is, you hear that thud. That thud is non-mechanical energy. Okay, so the inelastic collision that we have here, okay, kinetic energy is not going to be conserved because of that thud and that sound that goes into that. So anytime you hear sound, that's non-mechanical energy, and it takes energy to make sound. So, all right, rest of the time is yours.